On March 2nd, 2026, the most valuable chip company in the world just dropped $4 billion in a single day. And, they didn't spend it on microchips or software or server racks.
They spent it on light bulbs. Well, microscopic lasers to be highly specific.
Exactly, because we are quite literally hitting a brick wall made of copper right now. And the entire AI industry is scrambling to replace the physical circulatory system of the internet with light.
Yeah, I mean, we've spent over a century optimizing how we move electrons through copper wire. It built the modern world, really. But the physics of copper are now the defining bottleneck of the current technology landscape. We are transitioning from an era constrained by computing power to an era constrained by data transmission.
Okay, let's unpack this. Our mission for this deep dive is to explore the massive, multi-billion-dollar optical supercycle that's currently reshaping the artificial intelligence industry. We are looking at a giant stack of recent sources today to do this.
Yeah, we've got high-level financial reports, FTC acquisition approvals, incredibly detailed technical specs, and even some pretty heated Reddit threads.
Right, to really understand this high-stakes gold rush. Because the biggest companies in the world are fighting to control the physical plumbing of AI.
And it really all comes down to the physics of scaling. As AI models grow exponentially, these massive data centers have to connect tens of thousands of GPUs together so they can act as a single massive brain.
And copper simply cannot handle that volume of traffic anymore. I was looking at the physical limits here, and it is actually fascinating.
Oh, it is. When you try to push data rates past, say, 400 gigabits per second over a copper wire, the metal itself turns against you. You get what is called the skin effect.
Where the high-frequency electrical signals get pushed to the very outer edge of the wire, which increases resistance, right?
Exactly. The signal degrades rapidly. So to compensate for that loss, data center engineers just have to pump in more and more power.
And all of that excess electrical power has to go somewhere. It basically dissipates as heat.
Right. And we aren't just talking about a warm server rack here. The heat density in these next-generation AI clusters is staggering.
So you have failing signal integrity alongside a severe overheating problem.
Exactly, which requires massive liquid cooling infrastructure right next to your incredibly expensive GPUs. I mean, the power demands of a single modern AI data center can rival a small city.
Wow.
And a huge percentage of that power is just being wasted trying to push stubborn electrons through copper.
So the industry is turning to photonics, moving data using photons, so light instead of electrons. But how exactly are they doing this at a microscopic level? I mean, you can't just blink a tiny flashlight on and off 400 billion times a second.
No, you definitely can't. They use what is called an electro-absorption modulated laser, or an EML for short.
Oh, yeah.
Instead of turning the laser itself on and off, which is far too slow and creates instability, the laser just stays continuously on. It fires a steady beam of light.
Like a constant stream.
Exactly. And in front of that laser is a microscopic modulator acting like an ultra-fast electronic shutter.
It takes the electrical signal from the AI processor and uses it to absorb or pass the light, instantly translating the data into light pulses.
And those pulses are then fired through incredibly thin strands of fiber optic glass, which means near instantaneous transmission with basically zero signal degradation over these distances.
Right, and radically lower power consumption because glass doesn't resist light the way copper resists electricity.
Right. But let me ask you this. Is this just an incremental upgrade? Like, is this like upgrading from a dirt road to a paved highway? Or is this more like abandoning cars entirely to use frictionless maglev trains?
Well, what is fascinating here is that it is absolutely a total paradigm shift. It is fundamentally changing how data centers are built.
Really? How so?
Historically, optical connections were strictly used for what the industry calls scale-out networking. You used lasers to connect one data center building to another building miles away.
Right, like long-haul internet cables. Exactly. But once you were inside the building, you switched back to cheap copper. But the sheer volume of AI data is forcing a shift to optical scale-up.
So the lasers are moving inside the house.
Yes, we are seeing the replacement of ultra-short copper cables that connect servers within a single rack. The light is moving closer and closer to the processor itself.
Okay, so if the physical medium of the internet is changing, getting those lasers to actually talk to the GPU becomes the most valuable problem in the world.
It really does.
Which brings us to that single day in March. NVIDIA invested $2 billion into a photonics company called Lumentum, and another $2 billion into a competing photonics company called Coherent.
NVIDIA understands that their next-generation AI platforms are completely dependent on these laser components. They aren't just buying stock with that $4 billion.
What are they doing then?
They are securing multi-billion-dollar purchase commitments and funding new fabrication facilities. By pouring capital into the top two competing suppliers simultaneously, NVIDIA is aggressively de-risking its supply chain.
Oh, so they treat optical capacity as a critical strategic reserve. Kind of like how they partnered deeply with TSMC to ensure they never run out of the silicon chips themselves.
Precisely. But securing the raw lasers is only half the battle. Getting those lasers onto the motherboard creates a massive real estate problem.
Right, because you have all these fiber optic cables converging around the GPU. They're taking up physical space where designers desperately want to put more high bandwidth memory.
Exactly, and that bottleneck explains the next major move we saw in the reports. Marvell Technology acquiring a startup called Celestial AI for $3.25 billion.
Yeah, that breaks down to $1 billion in cash and $2.25 billion in stock, plus massive earnouts. That is a huge bet.
It is, but Celestial AI cracked a major code with a technology they call the photonic fabric.
Right. The technical details in the acquisition report revealed they managed to deliver 16 terabits per second of bandwidth in a single compact chiplet.
To put that in perspective, that is 10 times the capacity of today's absolute state-of-the-art 1.6 terabit ports.
That is wild. And the really crucial part of the Celestial AI tech is the thermal stability, right?
Yes, it runs so cool that Marvell can vertically co-package it. They can physically stack this optical chiplet in 3D directly beneath the high-powered GPU.
So they don't have to route the connection out to the edge of the processor board anymore.
Exactly. They are plugging the light straight into the heart of the chip.
Which frees up all that highly valuable beachfront real estate around the edge of the processor.
Right. And if we connect this to the bigger picture, Marvell isn't treating this as a distant science experiment.
No, they are projecting this specific photonic fabric technology will hit a $500 million annualized run rate by late 2028.
We are looking at near-term commercial reality here, and it is expected to double to a $1 billion run rate the following year.
Which brings us back to the companies actually manufacturing the raw lasers that make all of this possible. The history of this specific sector is wild.
Oh, it is a total roller coaster.
I really want to look closely at Lumentum, the company that just got that $2 billion injection from NVIDIA. Lumentum was spun out of a company called JDS Uniphase, or JDSU.
Yeah, JDSU was the absolute poster child of the fiber optic boom in the late 1990s.
They were the darling of the dot-com bubble. I mean, their stock peaked at an $80 billion valuation in early 2000. People thought the internet was going to require infinite fiber optics immediately.
And then the telecom bubble burst, demand dried up, and they suffer one of the most spectacular crashes in Wall Street history.
Right, the stock went from $150 a share to under $2. Billions of dollars just evaporated overnight.
But from those ashes, the core laser component business was eventually spun out in 2015 as Lumentum.
And today, Lumentum is an AI darling again. They were just added to the S&P 500, and their stock has surged an incredible 966% over the past year.
The financial reports show that surge is backed by genuine market dominance, though. Lumentum's Q2 revenue for fiscal year 2026 hit $665.5 million.
Which is up 65% year over year.
Right. They currently hold an estimated 50 to 60% market share in those incredibly fast EML lasers we talked about. They manufacture these chips using a material called indium phosphide.
I was reading about that. Why use indium phosphide instead of standard silicon? I mean, the entire computing industry is built on silicon.
Well, silicon is phenomenal for processing data, but it is physically terrible at emitting light.
Oh, really?
Yeah. Indium phosphide is a specialized compound semiconductor. When you pass an electrical current through it, it efficiently spits out photons at the exact infrared wavelengths that travel perfectly through glass fiber without scattering.
Like 1310 nanometers, right?
Exactly. And right now, as the industry transitions to next-generation speeds, you need an indium phosphide laser capable of pushing 200 gigabits per single lane.
And Lumentum is essentially the only supplier shipping those 200 G per lane devices at massive volume. But wait, Lumentum is trading at roughly 90 times forward earnings right now.
Yeah, that is a very steep valuation.
That prices in absolute perfection for the next decade. How are institutional investors justifying that kind of multiple without fearing an immediate crash? I mean, that sounds exactly like the setup for the JDSU.com wipeout you just described.
Well, financial analysts have a very clear bear case outlining those exact risks. Beyond the extreme valuation, Lumentum is carrying a $2.56 billion debt load.
Mostly from past acquisitions, right?
Right. And that is a heavy burden for a hardware manufacturer operating in a capital-intensive industry.
So what is the biggest physical threat to that valuation?
It comes from their main competitor, Coherent.
Coherent being the other company NVIDIA just handed $2 billion to.
Exactly. Coherent is actively ramping up a massive new fabrication facility in Texas.
Right.
Currently, Lumentum manufactures its indium phosphide laser chips on wafers that are 3 inches in diameter.
Right.
Coherent's new facility is designed to produce these chips on 6-inch wafers.
Oh, wow. So they are doubling the size of the wafer to stamp out more lasers.
It is actually much more than double. The geometry of semiconductor manufacturing is ruthless. A 6-inch wafer isn't twice as big as a 3-inch wafer.
Because of the area formula.
Right, area equals pi times the radius squared, so a 6-inch wafer has 4 times the surface area. Plus, the curved outer edge of any circular wafer wastes chips.
So a larger circle has a smaller edge-to-area ratio.
Exactly, meaning the usable yield is even better than 4 times.
And it takes the exact same amount of time for a machine to process a 3-inch wafer as a 6-inch wafer in the clean room.
So labor and machine time per chip basically plummets. If Coherent perfects the yield on those 6-inch wafers and catches up on the 200G performance, they could flood the market.
Which would instantly crash the scarcity pricing that is currently propping up Lumentum's 90 times earnings multiple.
Right. It's a huge risk.
Okay, so Lumentum Coherent are the heavyweights battling over the raw laser chips. But there's another massive bottleneck in the supply chain that I want to look at.
The assembly bottleneck.
Exactly. How these microscopic components are actually assembled. I want to look at the agile, smaller players trying to revolutionize the manufacturing process. Specifically, a company called POSE Technologies and their recent partnership with SIVE Semiconductors.
Building an optical transceiver traditionally requires taking dozens of microscopic, discrete components like lasers, modulators, and multiplexers and physically aligning them.
And doing that manually is ridiculously expensive and incredibly prone to faults.
Extremely. If one microscopic piece is misaligned by a fraction of a millimeter, the light escapes and the whole unit fails.
So POSE's solution to this assembly nightmare is something called an optical interposer. They basically figured out a way to integrate everything on a single wafer scale.
Right. Instead of using tweezers and microscopes to align parts, they use semiconductor manufacturing techniques to print the microscopic optical pathways directly onto a base layer.
Which makes the final technology 75% smaller and drastically cheaper to produce because you eliminate the active manual alignment.
And in this new partnership, SIVE Semiconductors is providing the lasers that plug into POSE's interposer. SIVE specializes in high-power distributed feedback lasers, or DFB lasers.
I saw that acronym everywhere in the specs. What makes a DFB laser different from a normal laser?
Well, if you fire a standard laser down a long fiber, the beam actually consists of multiple slightly different colors or wavelengths.
Okay.
Over distance, these different colors travel at slightly different speeds. They spread out and blur the data signal, which is called chromatic dispersion.
Ah, so a DFB laser fixes that.
Yes. It has a built-in microscopic grating that acts like a physical filter. It forces the laser to emit one pure, incredibly narrow, single color of light.
Which guarantees perfect clarity. That has to be crucial when you are cramming terabits of data through a single fiber.
Yeah, absolutely crucial.
So to use an analogy here, traditional transceiver assembly is kind of like painstakingly gluing together 50 custom action figures to make a diorama. It takes forever and breaks easily.
That's one way to look at it, yeah.
Whereas POET is basically providing a universal Lego baseplate where SIVE's ultra-pure DFB lasers can just seamlessly snap into place.
That is an excellent way to visualize a modular, highly scalable solution, and the market implications here are significant.
Definitely. We know Celestial AI, the company Marvell just bought, is a major customer for POET. They are projecting a potential $400 million in revenue just for POET's components.
Furthermore, POET is also sourcing components from Lumentum, integrating themselves deeply into the broader ecosystem.
I was digging into the market dynamics around POET on retail investment forums like Reddit, and the tension is fascinating.
Oh, the retail versus institutional divide.
Right. There's a massive psychological divide here. POET is sitting on a reported $300 million cash pile, and institutional investors recently poured in $150 million buying shares at $7.25.
But the retail investors on these forums are highly frustrated by the wild daily stock volatility.
Exactly. There are rampant theories in the community that the stock is being heavily manipulated and shorted by hedge funds. We're reporting this objectively, of course.
Yeah.
But the frustration is very real.
The mechanics of investing in pre-revenue or early revenue technology companies always create this divide. Institutional investors look at the macro trends.
Right?
Analysts estimate the external light source market, which Puett is targeting, could be over $1 billion annually. Institutions are willing to park their money and wait for early prototypes to transition into high-volume commercial production.
Which Puett targets for the end of 2026.
Exactly.
But retail investors watch the ticker every single minute. When they see unexplained drops in the share price of a tech company that hasn't posted massive earnings yet, panic sets in.
It does. The perceived short selling creates an incredibly tense atmosphere, even when the underlying technology and institutional backing appear solid.
It is a brutal waiting game for volume production.
The price discovery of early-stage hardware companies is always volatile.
Okay, we've talked about terrestrial data centers, we've talked about the motherboard real estate, and we've talked about the wafer math of the laser supply chain. Here is where it gets really interesting.
Oh.
I was reading through recent regulatory filings, and the FTC just granted expedited antitrust approval for Elon Musk to acquire a startup called Mesh Optical Technologies.
Mesh builds highly energy-efficient optical transceivers. They were actually founded by former SpaceX engineers.
Right, so why does Musk want to bring them back in-house? It is entirely focused on a concept called StarMind.
StarMind was a central component of SpaceX's recent initial public offering commitments. The strategic vision is to build a space-based artificial intelligence data center network.
By launching 1 million low Earth orbit satellites.
Exactly.
When I first read about putting data centers in space, I'll be honest, it sounded like pure science fiction. Why go through all the incredibly expensive trouble of launching server racks on rockets when we have millions of acres of perfectly good land here on Earth?
It sounds crazy until you look at the power grid data.
Yes, exactly. To train the next generation of AI, you need gigawatt-scale data centers. A gigawatt is roughly the amount of power needed to run the entire city of San Francisco.
And finding a plot of land near a major city with a power grid capable of handling an extra gigawatt of continuous, uninterrupted draw without collapsing the local infrastructure, it's becoming physically impossible.
So space removes terrestrial real estate and power grid constraints entirely.
Above the atmosphere, you have access to continuous, unobstructed solar power. You also have the natural cooling of the space environment.
Which mitigates that massive heat density problem we discussed earlier.
Exactly. But taking computing infrastructure to orbit raises an important question. How do you connect 1 million satellites moving at 17,000 miles per hour so perfectly that they act as a single, unified AI brain?
Because you obviously can't run physical fiber optic cables between them.
Right.
You have to shoot the lasers through the vacuum of space.
Free space optical laser communication. That is the core expertise of Mesh Optical Technologies.
So Musk is systematically building a fully vertically integrated space computing empire.
Yes. He acquired Cursor to handle the AI coding software. He acquired Mesh for the free space optical hardware.
And he partnered with Anthropic and Google for underlying computing resources.
He is controlling every single layer of the stack, from the code generation down to the orbital lasers firing across the vacuum.
So what does this all mean for you, the listener? We started by talking about the copper wire failing us, creating a massive heat and data bottleneck on Earth.
And we ended up with 1 million satellites firing lasers at each other in low Earth orbit.
Exactly. The next time you open an app and use an AI tool to write a complex email or generate a high-resolution image, the answer you receive back was almost certainly generated by millions of tiny lasers flashing across microscopic optical interposers.
The data is bypassing the physical limits of the copper world we used to live in, traveling on beams of light.
It is a profound shift in how human infrastructure operates.
It really is. But it leaves us with a final lingering question to consider. We are currently spending billions of dollars replacing copper with light because electricity simply became too slow, too hot, and too inefficient to keep up with the demands of artificial intelligence.
Right.
But those AI models are continuing to grow exponentially, requiring faster and faster data rates.
Yeah.
At the rate we are going, what happens in a few years when we hit the absolute physical bandwidth limits of light itself? How will we build the next generation of intelligence when we simply run out of physics?
Wow. That is a thought that will keep you up at night. The data center X-rays showed the copper veins were failing, so we built a new circulatory system out of light. But even light has a speed limit. Keep exploring that invisible world of powering our tech, everyone. It's moving faster than you think.